Good afternoon, everybody, and welcome to our 18th edition of the Code of the Month. Today, we have the pleasure to have as guest Martin Krumblicher from Ruhr-University Bochum. He's the coordinator of the deal.II COE, and he will present us backgrounds on the deal.II finite element library. I think you've also explained why the coincidence is the name of the COE and the code is not the coincidence. So Martin, the floor is yours.
Okay, thank you all for coming, and I apologize because I'm the cause for the switch in the system. I had some technical problems. So let me talk about the deal.II finite element library and our applications in the COE. So to start with, I would just like to go to the COE for a few seconds here. So we have the COE deal.II-X, which is an exascale framework for digital twins of the human body. And we aim to provide models for various aspects of the human body based on mathematical abstractions in the deal.II library. We are targeting digital twins in organs in several aspects. I just have a picture here for the heart and the lung, but we have several more. I will show you a bit more about them later. I just want to mention that we are a transnational consortium which sits in 4 countries beyond Germany from my own institution. We have partners also in Italy, in France, and in Belgium. And yeah, that's kind of where we are acting. And I would like to go on the mathematical aspects of this framework, which is the deal.II library. And just before I start, let me just summarize a few things that we are doing with this library already. We are a new center of excellence, and we just started a few months ago. So we actually have previous work that we built upon. And just let me show you some of the applications. One of the applications I mentioned before is the heart modeling. We have the group in the Politecnico di Milano at MOX who are working on this topic here in the group of Luca Dede. And we're trying to get a multi-physics simulator for the heart, and we are kind of having several models that we want to target: electrophysiology, the mechanics of the heart, and of course various aspects in the blood dynamics eventually. So there's a lot of things going on in this area. They have their in-house code dealii-X. It's a library based on deal.II. So as I told you, we are having this as a backbone, and we want to especially leverage some of the HPC modules in deal.II, which I'm going to talk about more later. So essentially, kind of we're having this simulator at a partner in Milan, and they're trying to improve efficiency by doing our library and of course enhance support with this model. A second model that we're working on is the human brain. I have a group here from Erlangen in Germany. So Silvia Budai, Paul Steinmann, and Alexander Greiner are the ones working on this. And essentially, they are trying to look into biomechanical response in certain areas of the brain. They have various models that they've developed. So there's some viscoelasticity, which is involved there. And they are trying to identify parameters, which leads to very large spatial resolution requirements. Of course, what you see in the pictures here is the preliminary work before we're trying to apply these methods. And of course, in this application, we also have the verification in terms of experiments to some extent in this field. So really trying to challenge the algorithms going towards exascale and at the same time going towards verifying the models that we're using. Another model just going on in my list of human organs is the liver, with a group in Berlin, with help by Luca Heltai in Pisa, who look into the biomechanical properties of tissues. The main model here is also some elastodynamics. The important part about, of course, in many aspects is the non-invasive property here. And in this case, kind of the solid of the liver interplaying with fluid vessels at different scales is an important question. And of course, there's many unassessed properties that really claim for large-scale computations. I mean, just to mention the models, it's immersed methods that people are using. There's Lagrange multipliers involved, and eventually also multi-dimensional models which are going to be coupled with each other. By this I mean that we have a 3-dimensional model of the liver, but then we model certain vessels, certain aspects as 1-dimensional models in order to save computational time and actually make it tractable even on the largest scale computers. And just to show you a few things that people in our group, in the group in Berlin, have done. So there is some 3D 1D model, which is kind of displayed here in the middle. There is some preliminary work here and some stiffnesses that they have tried to determine. And this is where the work is going to be intensified in the following months. Okay, I hope I gave you some glimpse of the library usage. Now I want to go to the library itself and explain you where it comes from. deal.II is a software which is targeting the development of adaptive finite element codes. The name of deal.II is actually Differential Equations Analysis Library. This is abbreviated to deal, and then it's called deal.II because it's actually is a mathematical software which is in the second edition. I mean, there was a first edition in the early 1990s, which was not as successful, and then there's this new library, which is by now more than 25 years old. So it's actually an old software, but we have evolved it over many years. It won the 2007 Wilkinson Prize, and maybe something to brag about from more recently is that we got this IMACM Prize in Computational Science and Engineering this year on deal.II. So this is actually a very successful project. It's a library hosted on GitHub as many codes. I just counted this morning about the size of the code. I just tend to count the C++ code without comments and white space. And we have 46,000 lines of code. We have, of course, configuration through CMake, as many projects have, and a lot of tests. Maybe before I mentioned that, I mean, tests are 70,000. I didn't really count all lines exactly, even though there is a number here, but it's difficult to count with the tools. I mean, I could exaggerate, but I really don't want to. Interesting is also that besides the code in the library, we also have around 70,000 lines of code and more than 100,000 lines of comments in the tutorials of deal.II. So this is eventually amounting to 89 tutorial programs which show various aspects of the library and certain applications. Let me go on a bit with the community to show you who we are. I mean, deal.II, as I told you, it is an old project. It was started in 1997, so that's almost 30 years ago by now. It was started by 3 people at the Heidelberg University in Germany. Today, it's a very international project with 13 principal developers, which are the people who are leading the project. Of course, there's many contributors. The last time I checked was 418 individuals contributing to the library and around 90 or 100 who contributed in the last year. As I told you, I mean, we have this project. I mean, it started in Germany. Many of the people actually moved on to the US, but we have a solid EU base on this model with several Italian colleagues, Luca Heldai and me in this Center of Excellence. And then we have several more people in Germany and collaborators all around in Europe who are working with us. So I think this is really a very good example of our code. Just quickly, I mean, of course, we have a web page. We have several announcements on this web page. We have several tutorial programs. I really don't want to kind of go into them step by step because this is really something you can look at. I mean, we're going to share the slides. As far as I know, there's links on this various aspects here that you can check out if you're interested in them. So I want to just show you the principle of the library. I told you from the beginning that this is a library. It's not really a solver, and for many of our application people, this was actually a kind of a certain threshold in the beginning, because deal.II is not the program which solves your viscoelastic property equations. It really is a mathematical toolbox, you could say. It does not implement any equations. We don't even implement Poisson equations, even though I will show you several results of them later. But what we do in deal.II is we provide building blocks that make it easy to build such a solver for your own model. We are having the mission that we're trying to apply the methods to almost any partial differential equation. Of course, there is always some limits, but the essential properties that we need is you need some weak form, and you need to be able to express it in a certain C++ abstraction layer, put it like this. So we have C++, we're using a lot of templates. I will show you a few examples quite in a minute. And the main goal is that when you write prototypes of something more simple, so you want to test some models, you should be able to do this in a few hundreds of lines of code. Of course, you won't make your viscoelastic solver for the human brain, where we want to explore some inverse parameter estimation in these lines of code. But essentially, we're trying to simplify life, of course, always with the balance that whenever you abstract away something, that some users might lose something. We have many people actually starting from tutorials, even though many of the solvers that I'm showing you are actually bigger than this by now. The deal.II library, as I told you, it's kind of centered around the partial differential equation setting. So we're having a finite element infrastructure. So we're providing elements of continuous kind, discontinuous ones, which are the ones that many textbooks teach. We also have H-curl and H-diff conforming spaces, which are more advanced spaces in terms of certain mathematical problems. For example, when you have incompressible flows, you would like H-diff. When you have electromagnetic waves, you have H-curl, and so on. We have support for scalar vector value problem. You can combine them in whatever way you want. You can do adaptivity, both in terms of the mesh size H, in terms of the polynomial degree, or both of them. It really has certain infrastructure to support them all. We have support for all mesh types, even though we kind of have a specialization in history on line, quadrilateral, and hexahedral elements from the past. But since around 5 years, we also have support for simplices and mixed meshes. I still call it initial because there is certain features which are not as well developed, and we're pushing some of them with our COE. So it really is making progress a lot in this area. Pre-post processing is not done in deal.II itself. It's mostly done by other infrastructure software, for example, for visualization. Many of us use ParaView or Visit. Another topic is, of course, the backends. The linear algebra in deal.II is done by some built-in linear algebra for certain functionality. We have some sparse linear algebra that we have access to. We, of course, interface to LAPEC and all the basic things. We interface to Betsy. We have Trilinos, AMFPEC, Sundials. I have a few more examples in a few minutes, but we really have a lot of infrastructure there. And we parallelize this. We have done this on MPI and several hundreds of thousands of cores. I mean, we have GPU support, and I have a few slides on this later. So this is really what we are. When you solve a problem in deal.II, you kind of need to be aware with the finite element terminology, and many of our users in the Center of Excellence and also beyond are actually coming from a background either in engineering, physics, or mathematics, and for them it's pretty obvious how you would build it up, of course. Not everyone is doing this, since we're also going towards medicine, so I have to talk about this more later today. But just mentioning it, when we think about the problem, we think typically about triangulation, kind of a mesh, where we have the elements. On the mesh, we define a function space. Sorry, is there any problem?
No, please go on.
Okay, so we have a mesh, and on the mesh, we define a function space, which is kind of the mathematical definition of the finite element. When we have finite elements, they are eventually leading to something which is called the DOF handler in deal.II. So essentially, when you have functions on an element and the mesh of elements, you kind of collect the global number of degrees of freedom. Depending on the continuity of the function space, you might have one or more degrees of freedom shared between elements. And once you have that one, you actually start thinking about computing finite element integrals. For computing finite element integrals, you actually need 2 more ingredients, or 3 in the deal.II language, which is on the one hand the mapping. The mapping is kind of a description of deformed elements because we have complex geometries. The deformation is again something coming from the manifold and the mesh elements. So this is another ingredient. And of course, we are computing integrals. We are approximating them with a quadrature formula. There is an infrastructure called FE values in deal.II, which kind of combines those. But of course, this is something that's going to be relaxed in many other applications. And from them, we can build a linear system and solve the system with anything. I mean, have Betsy and Trilinos here on purpose. I mean, I'll show you a bit more results later. And then we output the result with another program. So this is essentially the features that we have. You can do everything which is on the black boxes here in deal.II, whereas the gray boxes are kind of the interfaces going somewhere else. And when you want to set up a Poisson problem, now I don't expect you to read the whole code here, but I really just want you to kind of get a glimpse here how it is coming together. So in this case, we would set up a grid here. It's a parallel computation. So we have MPI convert as a simple example of a communicator in parallel. In this case, we are selecting a two-dimensional problem with polynomials of degree 3. So here we are just having a template. So I told you we are using templates to provide specialization. So essentially a two-dimensional grid is something else than a three-dimensional grid, which is why there is this parameter. We can read the grid from a file. In this case, I have some external grid here. I set up a finite element. In this case, it's a quadrilateral or hexahedral element. It's quadrilateral because it's 2D actually. We put it of a degree 3 here. We define a quadrature formula, which is a Gauss quadrature in this example. We use a minimal one, and then eventually have a linear mapping because there is a 1 here in the mapping argument. And from this, we can set up the DOF handler, just going in sequence from the picture on the right. From the DOF handler, we need to enumerate the degrees of freedom which are actually happening on this computation. It synchronizes the things in parallel, whatever is done, so you don't see anything of the parameterization here. We set up some constraints. In this case, just for Dirichlet boundary conditions, we might have some advanced constraints if we do HRP or HP adaptivity. And then we just set up some vectors with some initialization of the vectors. I really just summarize this a little bit here. We initialize the vector based on the degrees of freedom, of course, and the parallel setup built into the mesh. So the mesh really determines the parallelization strategy. And from that, we could set up the finite element values, this object which evaluates the shape functions at the quadrature points and eventually computes contributions on the elements for the global program. And when you go into contributions, I mean, in this case, we really spell out the whole loop. So this is a very classical CPU-based program. We spell out how the element matrix for the Poisson problem would look like, how the right-hand side would look like for a right-hand side function of 1. Just to simplify things, of course, we can read it in from other functions or other fields or other simulation parts, even on a different mesh. But essentially, it's going like this here. Then you kind of read out the degrees of freedom on the elements, and then you translate this to the global scheme here. So this is how you can do it. Eventually, we need to do some MPI exchange in these functions, which are called compress, but it really is the only place which you need to change when you go from a sequential to a parallel program eventually. With that, we can solve a linear system. Now, of course, I really don't want to focus on the linear solvers too much because that's not our main specialty, but eventually you run a solver. In this case, we just conjugate gradient without preconditioning done from deal.II, and then we print out the data. So this is eventually all that you kind of need to know. The interface I should mention here, of course, we're not the only package in the world doing finite element abstractions. I mean, there is one which is very popular, especially from the language perspective, which is UFL. So this is a concept which grew out of the Phoenix project, and it's now used in many libraries, for example, Phoenix X, the newer ones, Firedrake, and others, where you really just write the weak form by a one-liner, whereas in deal.II you kind of do this shape gradients times JXW, which is kind of a summary for the determinant of the Jacobian times the quadrature weights. It's a complicated name. I certainly see the difference here. The reason why we still think it might be useful to have this language in deal.II is that we can specialize things and go into all of the details because we can modify everything, even the things which are abstracted behind shape gradients. I mean, shape gradients on a classical finite element problem are including transformations from reference to real coordinates and so on. This is the classical code that I've shown you before. We actually quite a lot of our recent developments in deal.II are using something which is a matrix-free code, where the matrix-free code is actually simpler in the sense that we are trying to express everything in terms of operations at quadrature points plus some pre and post steps here, where essentially we're just computing the action of a matrix on the terms here. In this case, there is some get gradient. Again, it's not as nice as the Phoenix language, we know this, but we have some flexibility, which is more difficult to get around in Phoenix because we can program this, we can combine it in any case as a programming language with a compiler, whereas Phoenix has this additional layer of Python, which might sometimes be beneficial and sometimes restrict you. So this is why we're doing this like more verbose in some sense, maybe less intuitive in terms of the mathematical language, but it gives you some power, which many of our application people like. Of course, when we talk about deal.II, we are going to apply them on modern hardware, especially since we are an exascale project. We're doing this on GPUs quite a lot on the recent years. So what we are doing is, we're kind of having this deal.II library as abstractions. We are writing then application codes, because for the COE, we're doing lung simulations, heart simulations, and so on. So we are using deal.II as an input oracle, you could say, for providing us some information. We maybe just control this infrastructure from deal.II in the application code. But of course, in many cases, we still need to develop in deal.II. And I told you, we have 2 of our PIs in the project are deal.II principal developers. And this means, of course, we need to have functionality in deal.II, because we have certain hardware features which might be done inside of deal.II, which we need to access when we want to improve algorithms. The mesh parallelization is another topic, which does not sit in the application usually, but in deal.II, or at least there is some helper functions in deal.II that we want to access with a linear algebra and so on. So our idea is usually that we try to separate the concerns in the sense that we're trying to put generic functionality in the deal.II library and develop them in the deal.II library, whereas we have the applications kind of controlling the simulations and using these features. And I really want to stress the last point here. We try to reuse this functionality in deal.II in many applications. And I told you before, we have these independent groups working on lungs and hearts and brains and livers and cell biology, which I didn't mention. So there's more in our CRE. And it really is working because we kind of can summarize the mathematical developments underneath it. So now coming to the software, and I told you, I promised you that we don't just use Betsy or Trillinos, which are American software, but we actually have quite a strong component in linear algebra doing in our own facilities of EU facilities. So we have PSC Toolkit as a sparse linear algebra library, providing us with certain features. I will come into them later. We have MUMPS also as a new feature that is integrated in deal.II, which provides sparse direct solvers. Let me mention them a bit later, but I really want to show you that this is something which the applications are usually not interacting with directly. Sometimes they do, because we are doing C++, we're providing wrappers or some interfaces, but often it's very much easier to just use the deal.II wrapper classes or deal.II interfaces, because then you can switch solvers. For example, sometimes PSC Toolkit provides the best solver because we really have a good team, but sometimes there is features which we really would like to use Betsy for. And then we can just switch to Betsy with a few type defs, essentially. So it's very easy to kind of make the switch in terms of the design that we're trying to use. Of course, we need to be careful how we set up the codes, but we try to use it in this way. And similar things is also going on with the hardware specialization. We really try to shield the application solver, for example, the brain solver or the lung solver or the heart solver, from abstracting the GPU architecture. So we do this sometimes, a few things we do in deal.II, we do quite some things with Cocos, but there really is this kind of separation also in terms of this functionality. And of course, when we do this implementation, sometimes in deal.II, sometimes we use external libraries like PSC Toolkit. We need to make the question when does it make sense to do one or the other? And we often have this question. We have external libraries specializing on certain aspects. For example, linear algebra and preconditioning is where they're really good at. Mesh partitioning is one where we are using just external libraries. We don't really do mesh partitioners because that's a completely different area where we don't have the main expertise within deal.II. Time stepping, of course, you should not write a time stepper by your own today, but you could use SandIELs, you could use Betsy TS or other infrastructures. The programming frameworks are similar. Of course, we're using MPI, but we use, of course, different aspects here. We use Cocos for quite a lot of functionality in GPUs, but not the only one. We have vectorization support from older infrastructure and so on. And really it comes together that sometimes we implement these things in deal.II when we feel that it's not enough what we get. So for example, we can have algorithms in deal.II for linear algebra because we don't have the available infrastructure. Of course, we have the short way to PSC toolkit, but we still might sometimes feel, okay, this is something that can be done when you know that this is a finite element algorithm that we need, which is why we have our own vector. We actually have a memory space on that vector as well to do different GPU types and host types in the same computation, but we have some defaults. We have SIMD abstractions for the vectorization, and we have several other separation layers. Okay, let me quickly use the next 10-15 minutes to show you one feature which is kind of big in deal.II, which is a matrix-free framework, which is used for solvers, especially multigrid. And with this, let me go here. I mean, when you do finite element problems on a big scale, then you usually ask yourself, well, where is your time spent? And when you look into solvers, at least if you do a classical route with BETSI or PSC toolkit, then you might see that, well, you spend most of your time in the matrix vector products with sparse matrices, or you do substitutions, which is related to the matrix vector product. So Gauss-Seidel or ILU or something like that could be the case. And the problem is that these kind of matrix vector products, they have a low arithmetic intensity. We could call it memory limited. So really the performance of them is not given by the compute performance, but by the memory bandwidth of the various architectures. So just to give you a number here, the algorithm is using like 0.16 to 0.25 flops per byte in terms of memory access versus arithmetic operations. Whereas many of the GPUs, especially the ones with tensor cores, they could do 20 flops per byte or even a bit more than this. Even if you have high bandwidth memory, which has like 3-4 terabytes per second, the tensor cores give you, I don't know, 50, 60, 80 teraflops per second on the same machine. And again, you make the ratio for 60 to 3, and then you see you arrive at 20. When you do higher order methods, which are useful for certain applications in our COE, it actually gets even more pressing because higher order methods have a more dense matrix because you have more coupling between degrees of freedom, which then just shows up in terms of the memory consumption that the degree 4 computation is maybe 10 times more expensive per degree of freedom as degree 1. You cannot really tune it very much because, I mean, of course, you could try to compress the column indices a bit, but it really is hard to tune it by a factor of 2. And the way out of this is, of course, to say, well, even if we make this assumption that the matrix vector product is the only operation, then you could say that a matrix-free algorithm could actually just say, well, I don't store the matrix because the memory transfer is the limit. Let me just recompute whatever is in that matrix. Since I have abundant compute capabilities, I might be faster. The idea comes from stencil-based computations. When you do finite differences, for example, you can do it also with finite elements in certain structures. But really, what we think about is the finite element integrals. So this is what I want to show you here. So when you do a classical finite element problem, as you see in the upper left part of my slide here, then you would say I assemble a matrix in one part of my code, and then I compute the matrix vector product in another one. And matrix-free is essentially just merging these two steps into one. So essentially just means that the finite element facility goes into the linear solver, so you need some abstract solvers that support this. I mean, for example, the basic BETSI Trilinus solvers do not straight out of the box support it. Of course, there is sometimes ways around it, but I just mentioned it that this is kind of abstracting things a bit. When we do the Laplacian operation in deal.II, we essentially just do this by looping over elements on GPUs. Typical CUDA code, for example, you use this a kernel here, so you really don't write the loop out explicitly. And then on each element, you would extract the local vector values. You apply the operations on the element without building this element matrix AE here. You really just make the action, which is why it's called matrix-free. And then you add the local result into global vector because you might accumulate integral contributions for certain degrees of freedom from several elements. We have done this in deal.II for maybe 15 years now. And we really have been focusing on kind of hitting a sweet spot in terms of data locality, arithmetic intensity on the one hand, but of course you don't want to have a high arithmetic intensity as its absolute guideline. We don't want gigaflops or teraflops or petaflops or exaflops on our machines. We want to have a fast solver, which is essentially leading us to the metric that we're optimizing for is the unknowns process per second. So how many degrees of freedom can we update per second, then it's typically gigadofs per second for the operator evaluations on recent GPU, one GPU models. So this is what we update for, which means that sometimes we do still pre-compute something and then access it from memory, but we always try to see what is a good balance. Of course, there's application demand sometimes in one direction and sometimes in the other. When you do it element by element, you really just express the finite element integral as a sum, and then on the sum you do various operations. I don't really want to go into details. I just show you that there is mathematical background to this where you can break it down. If you want to read it up afterwards from my slides, you can read it more here. You can express this actually as a sequence of 3 matrix vector products with S matrix, W matrix, and S matrix, where the W matrix is a diagonal matrix, which is the operation at the quadrature points. At least if you have a linear operator like Poisson, but you can do it for nonlinear ones with a nonlinear W instead. When you do a naive implementation with the integrals, so the basic deal-II facilities that I mentioned in the beginning can be used for doing this, then you would see a memory access, which is kind of proportional to these red lines on the left. So we gain quite a lot in terms of memory access against the matrix-based method for polynomial degree second and higher. So you gain a lot here. But of course, you do more operations, because this is what you classically learn, is that finite element problems in a very generic way profit from assembling a matrix. You do more arithmetic work. It's actually more just means now here vector, maybe a factor of 5 to 10 more if you have low order shape functions, and maybe a factor 3 to 4 more when you have higher order shape functions. So it's actually more expensive to do that. But there is actually one thing about it, that these naive interpolation matrices are not always dense or full rank. They don't are arbitrary. You can, for example, use the tensor product structure, at least if you factor away the geometric terms from the deformed elements. You get the tensor product form and work with them. This is an idea which is old, comes from the 1980s from spectral element community, where you just say that, well, when you want to do this interpolation from the node values or from your whatever the basis functions are representing, I should just mention that we have non-nodal basis functions in deal-II. But when you go that way, you should try to use tensor products, and on quad and hex elements, you can very easily do so. And eventually it boils down to one-dimensional interpolation operations instead. So when you want to go from node values on the left here to values at quadrature points or derivatives as quadrature points, you would just do operations in the horizontal and vertical direction separately, which then just go as one-dimensional interpolation matrices. And you can see that this actually, the complexity when you want to do all of the S operations in your finite element problem, it actually goes from a polynomial degree to the power 6 to polynomial degree to the power of 4 in 3D. And this is something which is typically carrying polynomial order to the power of 3 degrees of freedom. So eventually the complexity per degree of freedom is linear. So the matrix-free code, when you evaluate it in terms of the arithmetic operations, so on the right-hand side, I have this new line here, which is the gray lines. So this algorithm is called sum factorization. You can actually beat the number of operations a sparse matrix needs to do. When you have deformed elements, the sparse matrix has different entries coupling all degrees of freedom within an element with each other and all neighbors, whereas the matrix-free is just operating on the degrees of freedom, and you see this linear increase, making it a very slight slope here. But you really see that there is a different order of magnitude here in terms of operations. Now going from the arithmetic complexity and the memory access to the performance, just show you that, well, you can actually reach this performance in practice. This is on a CPU system, but we see similar numbers on GPUs. I just mentioned here that when you have polynomials of degree 3, a matrix-free algorithm, I have here 3 flavors by the green, red, and blue lines. The blue line is finite difference-like operation, but you really see that you can gain a factor of 10 for polynomial degree 3 on the same mesh with the same operations compared to a sparse matrix. You can also gain with higher orders, which is actually quite interesting. When you do matrix-free and go to higher orders, you can do more degrees of freedom per second than a matrix can do with a linear shape functions, which is also quite surprising if you have not used them before. So bottom line is just that this is efficient algorithms, but of course, you can gain performance. But the question is, of course, how do we do this? I mean, I just show here, we have doing these operations in my group and in the group at IRC in Munich. We have done some optimizations on the GPUs of the SuperMOOC NG system, which has this Ponte Vecchio GPUs of Intel. We don't like them as much as the NVIDIA GPUs because they have some quirks, but we just show you here that we can actually also do the performance modeling on these machines. And you see essentially some numbers which are a bit similar to the CPU system from the generation before, but maybe a factor of 2 to 3 faster. Okay, that's this one. But of course, matrix-free algorithms alone are not helping very much because we need to solve systems in our human body problems. We often have nonlinear systems with complicated operators. So the question is, of course, matrix vector product is good, but which options do we have for solvers? For example, we cannot really use substitution, so ILUs or SSOR, something like that is very challenging in matrix-free codes, especially for the integration-based ones, because we never see a matrix entry in its final version. We cannot really build algebraic multigrid hierarchies because they kind of build on some operators and matrix-matrix products. So this is really something which is limiting. So yeah, well, we could use AMG, of course, for high order spaces, but then you need high iteration counts. So there is some work in the literature not done by us who actually use low order refined AMG for preconditioning. We often like something else. We can use multigrid solvers with some specific smoothers, for example, Jacobi type smoothers, which just need diagonal, or Chebyshev accelerations, if that won't work. You can do overlapping Schwarz, which is essentially just building element-wise or batch-wise inverses on approximations where you can actually use tensor product inversions, which is quite interesting. Of course, multigrid transfer between different grid levels or polynomial degrees is quite easy. Of course, we have a meshing infrastructure in deal.II, which is distributed. So this is just a picture here showing a computation on 3 processes. The upper part is how the global mesh would look like and how it is partitioned between the 3 processes. And on the top, on the bottom, you see how the 3 processes actually see the mesh. And you see that, of course, they see the part that they own, but then they also have one layer of ghost elements which are owned by the neighbors, which are locally present. And then you see something white around it. The white elements around it, they're just there for compatibility purposes, you could say, because essentially we just build a mesh out of the refined uniform mesh. So we just do the local refinement adaptivity, but really not representing the full mesh. Of course, this can be wasteful on applications where we have a very complicated coarse mesh, as we call it. So sometimes we do something which is called a fully distributed mesh, where we actually just store this blue part around the elements and not all the other elements which are far away from our process. So this leads to memory savings in case the mesh comes from a mesh generator. We can then apply this to multigrid in geometric ways. Of course, you can say that, well, when you have the hierarchy of mesh refinements, then we can do a multigrid solver on this. We have done this quite a lot in deal.II. We are actually not just doing multigrid in terms of the usual mesh coarsening. We also do polynomial multigrid. We do multigrid going to different spaces. So we have this auxiliary space discretizations also that we use for multigrid, for example, because they lead to better iteration counts. Just quickly mentioning here, if you do DG discretizations of Poisson, which is something which is the most natural space if you do incompressible flows, so Darcy or Navier-Stokes with incompressible fluid models, then you would see that when you do classical multigrid, you might get an increase in polynomial in iteration counts when you go to higher polynomial degrees. But when you do it with this auxiliary space, so the C meaning the embedding continues, discontinuous, doing at the finest mesh level, and you actually see that, well, actually you still see an increase at some point, but it's actually very low iteration counts in comparison. So it really gains you something, and it's robust for penalty factors and other parameters. We have applied multigrid on large scales, just showing you that it's scaled well on the old machines with CPUs, and we're doing similar experiments right now for GPUs and testing them. And to finalize, let me just use a few more minutes for showing some advances that the local developments in deal.II are providing us and where we're pushing things. For example, The matrix-free solvers that I talked about, they are working well in some cases, but we of course also need matrices in certain applications because we don't know the preconditioning techniques without the matrices sometimes, which is why we have the BSC toolkit advances. We have MUMS as a sparse direct solver, which is even more robust than an iterative solver in BSC toolkit or deal.II. And then we have other geometric multigrid solvers. Let me quickly go through it. BSC toolkit is a linear algebra package doing many preconditioners, abstracting away the data structures from the user such that you can easily use it. So this is really the main infrastructure. I mean, they have algebraic multigrid in various flavors. This is very successful in some applications and it scales very, very well on many GPUs. There's some library here in case you want to look it up. For sparse direct solvers, I mean, I told you that we really sometimes have the difficult systems, especially in our coupled scenarios where we don't know how to precondition them with an iterative solver. So then is the case when we do direct solvers. We have MUMS as a team in our COE where we're integrating their facilities into deal.II, and they are having recent success in low rank approximations because the problem with sparse direct solvers is that you have this fill-in problem, and it gets actually quite severe on 3D problems and coupled problems, which is why there's this low rank approximation. And actually people use, in their group, use mixed precision to improve the storage requirements. For multigrid, sometimes we don't really have the mesh hierarchy, which is then the case when we use agglomeration-based methods. The agglomeration-based methods are quite interesting because you really just put together elements in the neighborhood and then tell you, well, this is my coarse element. Of course, it cannot be treated by the classical methods. You need some more advanced techniques, and we are working on them a lot to integrate this in deal.II, because essentially what it leads you to is that you need some generic polygons that you're defining shape functions on. This is quite a departure from the classical simplex or quadrilateral elements that you have in a classical finite element problem. The other thing is how you generate these agglomerates. I mean, you can do this with metis, but it actually generates much worse results than R trees, which are geometrically close. Let me just show you here why they are important. I mean, two researchers in our COE have applied them to electrophysiology in the human heart. And you just see 4 lines in this figure here. And the upper 2 lines are AMG methods when you do certain parameters, whereas the lower 2 methods are the geometric multigrid with this polygonal strategy here. And what you see is that the polygonal strategy is actually more efficient. I mean, you see iteration counts here, but they really have similar ingredients in terms of the multigrid smoother and the multigrid operators. So essentially, it is actually faster by approximately the same factor as the iteration count went down, plus that it might have some matrix-free components applicable as well. So this is really a very good success that we got here, and we try to integrate in deal.II. And the last topic I want to mention here is that I said in the beginning that we're doing C++ programming, and some of us really like this because, I mean, this is where we can make the methods efficient. We can really go down to the foundations of the ingredients. But we have several users which are struggling with the deal.II syntax. I mean, I told you it's not so simple as Phoenix, and even Phoenix is too complicated for certain people, especially in medical applications, which is why we're kind of trying to develop also GUI-based interfaces. I just call it that non-programmers should get productive with deal.II and deal.II-X. They should be doing this by various abstractions. So what we're doing is we're having an interface where we can set up graphs and nodes which are connected with each other, and then you very intuitively guide the user to provide the input. And we do this not just on local PCs, but we really try to go to clusters as well. I mean, this is really work in progress where we try to apply these technologies easily for medical applications. So just to show you a figure here that my colleague Giuseppe has done a few weeks ago, we're essentially just setting up a triangulation. So this is kind of what you saw in one of my code slides. And it really just tells you kind of what the arguments that you need to put to the triangulation should be. You can label the triangulation, you can put some properties of the triangulation, and then you can say that I want to refine my triangulation if it's sufficiently simple. Or you can integrate with Gmesh or other facilities that we have. Okay. That brings me to the end. To summarize, I hope I've given you some insight into the development of this vibrant and active project deal.II. As I told you, it's providing mathematical formulations. It might be helpful also outside of our center of excellence, maybe in others, but really focusing on finite element problems and partial differential equations. And we support this development in our COE, and especially important is the solver question and coupled multiphysics problems. And with this, I would like to thank you for the attention and close this now. Thank you.